Okay, from now on for the next 2 weeks, I will say we'll start talking about the op amps or the operational amplifiers. Actually, the main difference between this device, which is actually an integrated circuit, most of the time you will see the abbreviation for an integrated circuit as the IC. And just a device, the integrated circuit has multiple devices in it. When I'm talking about multiple devices, I'm talking about multiple semiconductors, multiple active or reactive components in it. Means that we may have semiconductors, but in the same time we may have a set of resistors, set of capacitors, inductors in it. The operational amplifiers. Now I'm trying to explain one term at a time. For example, I will try to explain what means operational. We are looking for the mathematical operation, and that was the first the first idea how to make an operational amplifiers to perform mathematical operations. Initially, those operations was done with the electronics tubes. That's why it wasn't practical, and they want to make a small size of the circuits that it will perform different mathematical operations like addition, subtraction, integration, and differentiation. We'll talk about these type of circuits a bit later in this course, but I'm just trying to explain the name of these integrated circuits, and is the second term or terminology. It's the amplifiers. We know what means an amplifier. It will amplify, or it will have a gain in terms of the voltage, or in terms of the current, or in terms of the power between the input and the output. Now, just a short history about the integrated circuits. It was developed in 1965, and that's the mu A. That's the abbreviation, or that's the code for the first op amp, or the operational amplifier. It was made by the company which is the Fairchilds. We may see different symbols, like the first two letters for this type of circuits are not used intensively, because few years later they made an upgrade of the same operational amplifier, and they make the mu A741. Again, this is what we are looking for. 741 is an operational amplifier. It doesn't matter, the first two letters. The first two letters, actually, it will describe the vendor or the manufacturer that makes, the operational amplifier, the 741. We may see SN, MC, beta, A, or any other, letters in front of the 741. 741, it will define the operational amplifiers. Now, both technology are used. We know what means the BJT, bipolar junction transistor, and the MOSFET technology, metal oxide semiconductors. Remember that always, the MOSFET is for a low power, or it's for the high input impedance for the integrated circuits, or for the input impedance of the integrated circuit, or the op amps. Usually, or normally, we have 20 to 30 transistors. There is a small change in this basic or the first operational amplifier that makes, different operational amplifiers for different applications. In terms of packaging, we'll see, most of the time the dual inline package, which is abbreviated as DIP or DIP. Dual inline means that we may see, integrated circuit, which looks like, the first one, the second one, and we may see, 4 pins or leads in one side and the other 4 on the other side. In the same time, we may have the same operational amplifier, but on 8 pins, on 14 pins. Means that we may have a mini DIP package, which is the same op amp, but in 8 with 8 pins or leads, or we may have, the same operational amplifier with 14 pins or 14 leads for the package. Both of them are dual inline. We may see some integrated circuits that has a single inline, means that all the pins are in one side or on a single side of the op amps. Those op amps are not operational amplifiers, are just simply amplifiers that has the whole circuit for an amplifier in a single integrated circuit. Now, we may see some very small sizes, but again, relate, the small size with the amount of power or with the maximum current that can be delivered to a load as an SMT. Remember that SMD is the small surface mount device. SMT is the small or surface mount technology. That's, the only difference between the two abbreviation SMT or SMD. Now, if I'm looking on, the diagram of this integrated circuit, or the op amp, you notice that the pin 1 is always marked. It's marked with a key. You notice that I can have, that key dent in the case of the integrated circuit, or sometimes we'll have a dot. That white dot, it's always on the pin 1, and we are making, counterclockwise to label all the pins from 1 to 4 in one side, 5 to 8 on the other side. What else are you seeing, on this op amp? You notice that I'm having, the 2 inputs. One is the inverting input, and the other one is non-inverting input. Means that this operational amplifier has 2 inputs and a single output. The voltage sources, or the supplied voltage, you notice that I'm having 2 supplied voltages. One is labeled as the V plus, and you will see some other notation. Again, it's not standardized, how it's labeled or how it's or the notation for the positive voltage. And the other one is the V minus, which is the negative voltage. Means that most of the time when you are seeing an op amp, you will see a dual voltage source. And we'll talk, a bit later about, the dual voltage source and the advantage or the purpose of using, the 2 voltage sources. At this point, it's, the V plus and the V minus that is labeled in this diagram. NC is for no connections or no connection. That's why, some pins are labeled as the NC. Another pin is the offset null. We'll discuss a bit later about, the offset null and the meaning of the of this pin that may be used in order to make, the output level as 0 when the 2 inputs are connected to the ground. Now, the symbol, you notice that, in the symbol of the op amp is a triangular shape. And in order to differentiate the two inputs, one input is labeled with negative and the other input is labeled with the positive. What that means, the negative is the inverting or the negative label for the input is the inverting input, and the non-inverting input is labeled with a positive sign. What that means in terms of the phase shift, and that's the only difference between the two inputs. Suppose that I'm applying a negative signal on the inverting input. On the output will end up with a positive symbol. If we are applying a positive on the inverting input, on the output will have a negative value. What that means, 180 degrees out of phase between the input and the output. And that's the meaning of the inverting input. On the non-inverting input, which is labeled with that positive sign, means that if I'm applying a positive signal or a positive voltage on the non-inverting input, the output will be positive, means that there is no phase shift between the input and the output if the signal or the voltage is applied on the non-inverting input. Now, to remind you about, the meaning of those two inputs, inverting input is always with a negative sign, means that the output voltage is 180 degrees out of phase with the input inverting. For non-inverting, it will not have, any phase shift between the output and the input. What an operated circuit does, it will amplify the difference between the two inputs. And I will explain a bit later the amplification or the gain that is used in op-amps, that it will amplify the difference between the two signals or between the two voltages that is applied on the two inputs, inverting input and non-inverting input. Now, on the small size or the mini deep dual inline, we may see a single integrated circuit. We may see a V pulse, like positive voltage. I mentioned that there is not standardized, the notation for the negative and the positive voltages. We may see the dot, which always is placed on the pin 1 and going, clockwise. We may see two operational amplifiers or dual op-amps in a single integrated circuit. In this example, you notice that I'm having, the same size, the same shape for the op-amp, but has dual or two operational amplifiers in it, and shows, the two inputs and the output for each of the two operational amplifiers. We may see some operational amplifiers that has 14 pins, and some of them may have 4 actually operational amplifiers in it. As in this example, we have 4 operational amplifiers, and you notice that the V plus and the V minus has a different label as the VEE and the VCC. Remember that the VCC and the VEE is like borrowing, the notation from the BJTs. VCC as the positive voltage, the VEE as the negative voltage. We may see another notation from a MOSFET. Remember that in MOSFET, we used to have, the VDD and the VSS. That's, another way, or that's another notation that may be used in having, the two voltages, the V plus or the V minus. I mentioned that in op amps, most of the time we will see a dual power supply configuration. And this is what we are using in lab. Suppose that I'm having, the two voltage sources. That's why I made, a request, to have all the voltage sources as a dual voltage source. How to connect the two voltage sources to have a dual voltage source. One side is the positive, or one terminal that supplies voltage to the op amp. It's the positive power supply terminal, which is connected to the pin 4 in this example, and the other one, which is the negative, which is actually connected to the pin 11 in this configuration. If I have to supply the voltage to a very simple basic op amp, I will connect the positive, or the V plus, to the pin 7 and the pin 4 as the negative power supply to the op amp. The ground is used, for the output voltage with respect to ground. Means that the swing of the output voltage is anywhere between the positive voltage source and the negative voltage source that is applied to the circuit. And that's, an advantage of using a dual voltage source. Again, most of the time you are seeing a dual voltage source, not a single voltage source. Some applications, I'm not saying, all of them may use, dual voltage source. Some applications or requires just a single voltage source. Suppose that I'll make, a comparator with respect to 0 for all the voltages that are above 0. Means that I don't have to use, that negative voltage source. But I'm just showing, I'm just giving, an idea about where we may see a single voltage source instead of dual voltage sources. Again, it's based on the applications that may be using an op amp, a 741. You notice that in this basic circuit has the dual voltage sources, or the VCC and the VEE, which is connected to pin 4, and this is what we are using in lab. We are using just a mini DIP, means that 8 pins only, but in the same time I will show you the same op amp that is packaged in 14 pins. You notice that the negative of the two voltage sources, it's connected to pin 4, and the positive of the voltage source or the supplied voltage is connected to the pin 7. The ground is used for the input and for the output. The output is connected to a load resistance, that's the RL, in this example 10 kiloamps, which is connected to the ground. Means that the output voltage can be swing between the two, it's called rails, or rail to rail, and the output voltage can be anywhere between the positive VCC or the negative VEE. Now, we'll have, the same approach as we did with the other components. We'll talk about the ideal op amps, and that was, the key points, or, they want to create, a circuit, they want to make a circuit, they designed a circuit having, those, key points in mind. And after that, we'll switch to the real or a practical op amp, which has, some restrictions on these initial ideas to for an ideal op amp. We may see, the first require, for an op amp having an infinite voltage gain. Again, we have, a pretty large voltage gain, but not an infinite gain. But that was, the main purpose of integrated circuit or an op-amp. Infinite input impedance does not load the driving source or the source that is connected between the two inputs. It will draw the minimum current or it will draw no current. That's why an infinite input resistance. Zero output resistance. I know that is not possible because if the output impedance is zero, means that can be can drive any loads or actually an infinite output current, which is not possible. Infinite bandwidth means that we may have a flat amplitude or magnitude of zero, a flat magnitude for any frequencies between 0 and a high frequency. Zero input offset. Again, we'll talk about how to offset the output voltage when the two inputs are connected to the ground using that pin, the pin 1. That's the equivalent circuit for an ideal op-amp that has an infinite impedance, has an infinite gain, and has no resistance or no input, no output impedance on the output of the op-amp. Now remember that what an op-amp does, it will amplify the difference between the two input signals. You notice that in this diagram shows, a very basic circuit that has an op-amp. The V plus, V minus are like the two input signals. The V plus is the input voltage applied to a non-inverting input. The lowercase v minus is the input voltage to an inverting input. The output voltage or the V0 or the V out, it will amplify the difference between the two input voltages. Means that the V plus minus the V minus multiplied by the gain of the op-amp, of the operational amplifier. The V out, again, it's the gain. We notice that I'm using, that's why I introduced in transistors the symbol for a gain as the A. V is in terms of voltage, means that the gain in voltage multiplied by the V in, but in this case, that's a differential amplifier which amplifies the difference between the two inputs. Means that from this equation, I can rearrange the equation to find the equation for the AV or the gain in voltage as the V out over the V in. The two supplied voltages, I mentioned that we may use VCC or the VEE. That's from BJT notation. From a MOSFET notation, we may see the other two notations, for the VDD as the positive voltage and the VSS as the negative voltage. The output voltage or the V0, it will swing between the maximum positive and the minimum negative. Remember that the idea was, to create an integrated circuit that draws no current, or there is no current that flows into, any of the two inputs of the op-amp. That's why you may see a very large input impedance between the two inputs of the op-amp. That's the typical transfer characteristic. That's the output voltage, and I will make an example. What to expect and what to see on the output of the operational amplifier, when the output may swing, between the two rails. One rail is the positive VCC or the positive voltage. The other rail or the other voltage that is applied to the circuit as the negative voltage. Remember that when the transistor is in saturation, not always, the voltage in saturation is equal to 0. For a practical BJT, that voltage is about, 0.2, 0.4. We may see, 2 or 3, 4 transistors on the output circuit of the op-amp. That's why the output voltage is actually, or the maximum output voltage is actually the supplied voltage, and less by 1 or 2 volts. And I'll make an example, and I put, an example on the right side, means that suppose that the typical voltage for a 741 is 15 volts. The output voltage, it will be closer, or, around, plus 13 volts. And the minus 30 volts. I mentioned that we may see a different voltages or the supplied voltages for different op amps, and I'll discuss a bit later. Now, on a practical side, there is always limitations and from the ideal characteristics, and going to a practical or real op amps, the input impedance, it will have a very large value, like the impedance of 100 mega ohms, means that it's still a very high input impedance, which requires a very small amount of current. I'm talking about the few micro or nano amps, which can be approximated as a current of 0. The infinite open loop, again, it's very high, is in terms of 10 to power 6, but is not an infinite gain, but is a very high gain that can be used in our calculations, in our applications. The output impedance, you notice that the ideal has an output impedance of 0, but in practical or real op amps, it will have the impedance or the output impedance as or around 100 ohms. We may use these values in our examples, and I'm trying to stay closer or as close as possible to those real or practical values for the characteristics of the op amps. Now, how we can make, the amplifier model, to simplify the circuit, what is inside? We may see an input impedance as, 10 kilo ohms, 100 kilo ohms in this range, or, higher than that, depending on the type of the op amps. We may see a gain in voltage, which means that can be symbolized with a voltage source, and we may see a low resistance or a low impedance on the output of the circuit. In this way, we can make the approximation or the model for an op amp which has an input impedance and an output impedance in series with an ideal voltage source. Now we'll talk about the voltage gain, the resistance, the output impedance for a practical op amp. Usually, or the typical gain is around 100 or 140. 140 is one of the values that has or is specific for a certain family or a certain type of the op amps. Usually for 741, we may see, you know, something around, you know, this value or around, you know, 100 dB in a voltage gain. And you may see, you know, 106 dBs as a typical, or, you know, in this range as the mean of 90 or 95, a maximum of 108, 112, 110. But anyway, that's, you know, the typical value for a 741 in terms of the gain. Again, it's not an infinite gain, but it's a very high, or it's high enough in our applications. And most of the time, you know, those circuits that does not require a very high gain, because always there is a limitation between the gain and the frequency. And I will explain a bit later the relationship between the gain and the bandwidth or the frequency that an op amp, you know, can be used. In terms of the input impedance, I mentioned that ideally it's an infinite. A typical value for the input impedance is around, or it's about, you know, the 2 megohms. It's a very high impedance. That's for a BJT. If we are using an FET or a MOSFET technology or field effect transistor, we may see much larger values as 10 to the power 12 ohms. We may see, you know, the values of these op amps when we'll do, you know, the calculations for network. And that's, you know, the other topic that will introduce, you know, this week, the feedback network that is used in op amps. The output impedance, I mentioned that is around, you know, 100 ohms. Most of the time, the typical value is, you know, 75 ohms. And we'll stay, you know, close to, you know, these values, 75 or 100 ohms in our applications. Another limitation based on the output impedance is the maximum current. The maximum current that can be supplied to a load is 20 milliamps, means that always is the limitation of the op amps of the power dissipated, and in top of that is the maximum power, the maximum current that can be supplied to a load that is connected on the output of the op amp. In terms of the voltage sources, most of the time you will see a range, means that for the 741 can be connected between plus or minus 5 volts, plus or minus 18 volts. Usually, or the typical value for the supplied voltage is plus 15 volts. That's the most used voltage in using the op amps. Means that the op amp, it will work, you know, just fine if I'm supplying, you know, just 10 volts, or it works, you know, the same if the voltage is 12 volts. Some other circuits, which is still an op amp, can handle a larger voltage or a larger than 18 or plus or minus 18 volts. And I put an example here that we may see, you know, the op amps that are used in plus or minus 30 volts. On the lower side, you notice that the minimum voltage, because we know that all the transistors that has to be placed in the Q point or in a certain region of the load line, they may use, you know, a lower voltage, and that's, you know, for a lower voltage or a low consumption op amps that may be used for 1.5 volts as the supplied voltage. Again, the range that we may see between 4 volts and 30 volts, again, depends on the applications, depends on, the op-amps code or the op-amps type. But most of the time when we are seeing, 741, remember that it's, plus or minus 15, we can go higher to 18 volts. Some of the 741 may go higher to 24 volts. And you may see 741A as the code for the operational amplifier, followed by a letter or a group of letters as AB, AC, or BC, means that, probably, different voltages or different ambient temperature, can be used for those op amps. On the output voltage, I mentioned that it's determined by the type of op amp and the supplied voltage that it's used. Again, I made an example. If the supplied voltage is plus or minus 15 volts, the output voltage will swing between the positive 13 and the negative 13 volts. Means that we can have, a swing in an output voltage of 26 volts, let's say peak to peak. That's why always we have to make, the based on the supplied voltage, the output voltage is the supply voltage less by 1 or 2 volts. That's, a practical value. That's why I want to show you, and I put, an example what to expect in labs, what to expect in the practical value of the output on the op amps. The other type, which is the FET technology or the MOSFET technology, the maximum voltage, it's probably not, in terms of 2 volts, probably will be 1 volt or less than 1 volt when he's in saturation or as the maximum voltage. In terms of the frequency response, now you notice that if I will plot, the body diagram or what is the frequency response, for the op amps, you notice that for a low frequency has that very high gain, which is, 10 to power 6, 10 to, or in this range, dBs. As the frequency is increasing, there is a drop in gain. For example, the frequency is 1 megahertz, means that, the gain is almost 1, or the gain is dropping, to a very low value as the frequency is, 1 megahertz. And we'll make, another lecture, and we'll discuss about the product between the gain and the frequency, and we'll discuss, how to manage, the change in the gain as the frequency is increased. You notice that we may discuss about, the cut off. That's, the frequency that it will have, a drop by 3 dBs as the frequency is increased. Means that this frequency is very low, means that the gain is dropping as the frequency is increasing, which is not one of the best characteristics. And that's why I'll make, a common, bit later, how to manage or how to keep, the gain or the product between the gain and the frequency. Some high frequency device may operate to a very high frequency, like, gigahertz. You notice that the limitation of this op amp 741 for a basic applications, it's about, 1 megahertz frequency. That's why For large frequencies or for any other frequencies above megahertz or 1 megahertz, 2 megahertz, we may have to use, a different op amp or a different series of the op amps. Now we'll talk about, just briefly on the schematic diagram or what is inside of an op amp. You notice that I'm having, some transistors on the output. That is, the limitation when the collector emitter voltage, when it is in saturation, one of the two resistors, it will become, the 0.1 or 1 volt or 2 volts. And the two resistors that are added into the emitter of the last two resistors, which is the final stage or the push-pull circuit, that it will limit actually the output current. Those two resistors, again, are used to limit the output current, and actually it will prevent the short circuit or has a short circuit protection in it, having those two resistors and the other two transistors that are connected across the two resistors on the output. Basically, we're looking for 3 blocks or 3 sub-circuits on the op amps. Basically, we have 22 transistors, 11 resistors, 1 diode, and 1 capacitor in it. You notice that, and I mentioned an integrated circuit may have, multiple semiconductors. In this case, we have 1 diode and 22 transistors. As semiconductors may have multiple resistors. In this case, or in this example, 11 resistors and a capacitor. Now, some circuits may have, some small inductors in it, but most of the time we are seeing inductors as an external device, not an internal device, because internally we can make, we can build, just a small inductors. Externally, we may have, different values, for those inductances. Means that we have no limitations on, how to make, the inductances on the as an external device. In the same way for capacitors, those capacitors are very small capacitors, or has, very small capacitors. A large capacitors, always it will be on the external or as an external device. I mentioned that the 3 main blocks of an operational amplifier. The first stage is a differential amplifier input stage, means that it will amplify the difference between the two inputs, the V plus and the V minus, in terms of the input voltages. And the second stage is a voltage amplifier gain stage. That's the stage that it will amplify the difference between the two input voltages. And the last stage is called the push-pull amplifier that has the ability of providing a certain amount of current. And we discussed that. Usually it's for unusual or for a practical 741, it's 20 milliamps. The first stage, and we'll discuss, next lecture tomorrow morning, and we'll discuss, just, the first stage and how it's made, because we know how to model the differential amplifier using just 2 transistors. Is a bit more complicated in an op amp, but I will describe tomorrow morning the basic functionality of the input circuit, which is the differential amplifier used in op amps. The second stage, which is the middle part, is a gain is an amplifier, or it's called a class A amplifier. We may see class A, class B, class AB amplifier. And the last stage, which is, the last part of, or the last stage or the last sub-circuit of an op-amp, which is the push-pull, which is the final stage, I would say, of the op-amp. And I will end up, here. And tomorrow we'll talk about, the basic functionality of a differential input stage, or the input amplifier. And we know, these, two circuits, and we know how to approach, or how to describe, the basic functionality of the two circuits. And after that, we'll go with the different input voltages that can be connected on the two inputs of the op-amp. Any questions, comments, concerns, please? Or just 1 second, I'm showing, different op-amps. I choose, different op-amps or different packages just to show you always, there is a key. You notice that in this diagram, I'm trying, in this diagram, the key that it's used, for the first integrated circuit, I may try to use, this highlighter. You notice that there is a key. Always, the key shows you on the left side is the pin 1. Sometimes you may see a white stripe or a band which has, the pin 1 and pin 14 on the opposite side, but always, the key is again on the top. We may see some integrated circuits that has, no band, no stripe, but always, has the key. We are taking the key. On the left side of the key is the pin 1. That's, the pin 1. And sometimes you may see the key and a dot. Most of the time you'll see, the key and a white dot, because the color of the package is it's most of the time is black. I didn't see any other colors for the operational amplifier or for integrated circuits. Means that they may use the key and the white dot, the key and a black dot, or the key and a stripe, or just the key. You notice that that's the symbol for Motorola. That's a big one of the biggest companies in the semiconductors, and not only. That's the RCA. I don't know. I cannot see the other two, but anyway, that's the idea of placing the integrated circuits with 14 pins. And the other ones are with 18 with 8 pins. We may see some other integrated circuit that has pins on all 4 sides of the integrated circuit. Always, the pin 1 has a mark, has a dent, has a dot on the top, just to show you, the how it's labeled, how it's notated. Any questions, comments, concerns, please? If you don't have any questions, have a nice day, and I will see you tomorrow morning. Again, just to remind you about, test 1, test 2 is the same as test 1, 70% long type questions, around, I will say 4 plus or minus long type questions, and 10 multiple choice questions, 30%. Any clarifications, please, or any questions? If you don't have any questions, have a nice day.